We now make a connection between continuous time Markov processes and discrete time Markov chains. The state space is discrete in both of these situations. Okay, for continuous time processes, that's what we've been looking at up till this point in time. The time that the system stays in a particular state is exponentially distributed, and then it moves to a different state. So for the continuous time Markov processes, we have a rate matrix Q. The rows will sum to 0. We can get the limiting probabilities in a birth and death type process at least, and more generally we can get the limiting probabilities by solving the equation 0 is equal to pi times q. Now that's actually what we did when we found the limiting probabilities for a birth and death process. This is more general because we allow more rates. They don't have to be just on the superdiagonal and subdiagonal. And those limiting probabilities represent the long-run proportion that we are in the various states. We have something similar for discrete time Markov chains or discrete time processes. The system stays in a state for one step, and then it moves somewhere. It may move back to the same state that it is in, which is essentially not moving, but everything is counted in terms of steps. For the continuous time Markov process, we had a rate matrix Q. For the discrete time process, we have a probability transition matrix capital P. For the continuous time process, the rows summed to 0. For the discrete time process, the rows sum to 1. The limiting probability, we will use the same notation, namely a pi. And before we had to solve the equation 0 is equal to pi q to get the limiting probabilities. Here we're solving the equation pi is equal to pi times p, so it's a little bit different. We have a pi on the left-hand side. We have a probability transition matrix on the right-hand side. And the matrix P is going to be filled with probabilities. We can move from the discrete Markov chain to a continuous Markov process, or from a continuous Markov process to a discrete Markov chain. At least the same in the sense that we will get the same limiting vector pi for both processes. And we use a technique that is called uniformization. And going the two different directions is slightly different, so let's look at both of them separately. So first we will assume that we know the probability transition matrix P. We know that in order to find the limiting vector, we have to solve the equation pi is equal to pi times P. We can write the pi on the left-hand side as pi times the identity. And then we can move the pi times the identity over to the right-hand side, and we will end up getting an equation 0 is equal to pi times p minus I. And if we simply define q to be p minus I, you'll recall that the rows of P summed to 1, but now that we're subtracting 1s along the diagonal, the rows of p minus I, which we're calling q, are now going to sum to 0. All the entries are going to be positive except on the diagonal where all the entries will be less than or equal to 0. So we really do have a rate matrix now. Let's move the other direction. Let's assume that we have a rate matrix to begin with. We have to solve this equation, 0 is equal to pi q, in order to find the limiting matrix pi. What we do now is we define k to be the absolute value of the biggest entry in q. Normally that will be somewhere on the diagonal. And let's give it a name, we'll call it k. So we divide both sides by k. If you divide 0 by k, nothing happens. On the right-hand side, you get pi times q over k. Now we add a pi to both sides. So pi is equal to pi times I. So we're going to get pi on the left-hand side and pi times I plus q over k on the right-hand side. Now you will recall that q had negative entries on the diagonal. When we add the identity here, we're going to end up getting all the entries of q are going to be between 0 and 1, and on the diagonal they're minus values between 0 and 1. So when we add the identity, the rows will sum to 1. All the entries in P will be between 0 and 1, and that's exactly what we need for a probability transition matrix. Now, in our particular example, where we had two different types of customer, long and short, we were assuming the customers that took a short amount of time, again exponentially distributed, would correspond to a short amount of time corresponds to a larger rate. So mu1 has to be greater than mu2. So if we're trying to find the absolute maximum absolute value of q, lambda would be the increases. The bigger of the two mu's would be mu1. So lambda plus 2 mu1, if we had two servers working, lambda plus 2 mu1 would be the biggest possible entry. Maybe I'm wrong, maybe it won't even show up, but I think it'll lambda plus 2 mu1 shows up somewhere in absolute value. So somewhere on the diagonal of the q that we've been looking at is a minus lambda minus 2 mu1. So that's what we're going to divide by in order to get our transition matrix P. So P is equal to the identity plus q divided by lambda plus 2 mu1. The advantage here is we can now use matrix analytic methods that are written up only for the discrete Markov chain situation. It doesn't matter because we're getting exactly the correct limiting vector. And in Qiming He's book, Introduction to Matrix Analytic Methods, he basically assumes that he's working with a Markov chain, a discrete time Markov chain, and we can now do that and use the methods that he presents.